Hello everyone, it's a great pleasure to be here with you today. My name is Xiang. I'm a PhD student from Beijing University of Posts and Telecommunications. The paper I will be presenting today is about efficient inference in the IoT edge cluster. In the presentation, I will begin with the introduction of the parallel CNN inference and its challenges on the edge. Then I will elaborate our inference framework and show our experimental results. Finally, I will conclude the paper. First, let's begin with the introduction. Here on the left is a typical diagrammatic sketch of conveyors. A kernel slides over the entire input feature, and each movement will produce the pixel of the output. From the sketch, we can see that the computation of a kernel could be spatially parallelized. Thus, the common partition scheme is to divide input data into tails and distribute them to several local devices. The scheme is shown on the right figure. Note the light white line in the input cat image. It denotes the redundant partition, which will be detailed in the next slide. The partition scheme faces several challenges. The biggest challenge is the accumulated redundant commutation during inference. Due to the characteristic of conveyors, the partition scheme we mentioned has to introduce a redundant partition. For example, the figure here we divide the input feature into 4 tails. As the conveyor uses 3 multi-thread kernel, there are a pixel-wide layer of redundant partition on the edge of each tails and causes additional communication. Moreover, the additional communication will accumulate as the model size or the number of devices increases. Besides, the expensive communication at the edge requires a trade-off between communication and computation. And the heterogeneous edge environment is also a problem. Then I will introduce our pipeline cooperative inference framework BICO and how we solve those challenges. We introduce the spirit of pipeline into inference. Here is a sketch of our scheme. We optimize the inference process from 3 dimensions: data, model, and devices. We divide the CNN model into several segments, and those segments are assigned to several disjoint groups of the entire IoT cluster. The input data are processed through stages. In each stage, we divide the input data into tails with different sizes according to their computing capacity. Our optimization goal is to maximize the throughput of the entire inference pipeline. However, such an optimization faces many roadblocks. Each layer has different overhead for both communication and computation. The number of stages, the number of devices, and the CNN segment in a stage are all needed to be configured. In fact, we can show that find the optimal solution is NP-hard. Thus, we tend to use a heuristic approach, which first run dynamic programming in a virtual homogeneous cluster, then adapt the solution to a real heterogeneous cluster. Fortunately, a polynomial solution for homogeneous cluster exists and can be calculated using dynamic programming. We consider a homogeneous cluster with P devices and a CNN segment consisting of layers from I through J. From the optimal pipeline configuration at start, it now can be broken into optimal sub-pipeline consisting of layers from I through J dots with P minus E dots edge devices, which is here, followed by a single stage layer, J dot plus 1 through J replicated over P dot workers, which is here. And here is the dynamic programming formula. We can say it's a very simple iteration which iterates all the possible combinations of J dot and P dot. Here we show how to adapt the solution of dynamic programming to heterogeneous cluster. Given a cluster, first we need to build a virtual homogeneous cluster which has the same number of devices and the communication capacity of each device is the average of heterogeneous cluster. Then calculate S star using dynamic programming. Then for each stage in the optimal solution S star, we use a greedy algorithm to choose the same number of devices from the heterogeneous cluster and let the sum of their communicating capacity be similar to the original stage. Then we can use the divide and conquer algorithm to adjust the feature partition for each state, for each device according to their real communicating capacity. Next, I will show the relative experimental result to prove our contribution. Here we evaluate the throughput of both VGG and YOLO with 4 algorithms, and we can say Pico achieves best among those algorithms. And here we plot the CPU utilization and the percentage of redundant partition. And here we summarized our main contribution. That's all for my presentation. Thank you very much.